Welcome to this explainer. Today, we're going to explore the everyday magic of static electricity and uncover the invisible mathematical rules that literally govern the universe around us.
Okay, let's jump right into this. We're going to navigate this fascinating topic using these beautifully structured handwritten notes from DIA Physics. You know what I absolutely love about these pages is how they perfectly capture the beauty of physics in just its pure simplicity. We don't need a massive, heavy textbook today, just these clear, thoughtfully organized notes to guide us.
Here's our roadmap for today. First, the spark of electrostatics. Second, the rules of attraction. Third, the anatomy of charge. Fourth, charge versus mass. And finally, number 5, Coulomb's law revealed. All right, section 1. The spark of electrostatics, where we'll uncover frictional electricity.
The absolute foundation of our explainer today is electrostatics, which is simply the study of electric charge at rest. But hey, don't let the word rest fool you into thinking it's inactive or boring. This concept has massive real-world applications. The notes specifically call out how electrostatics is the foundational science behind the loudspeakers used to listen to music, electrostatic spraying of paints, and even fly ash collection in industrial chimneys to keep our air clean. It's seriously powerful stuff.
Moving right along to section 2, the rules of attraction. Opposites attract, likes repel.
The notes highlight some classic, elegant experiments to demonstrate these rules. Imagine you take a glass rod and rub it with some silk. Then you take a plastic rod and rub it with wool. The friction in these really simple actions actually generates two very different kinds of electric charge. It turns out there are literally only two kinds of charges in the entire universe, positive and negative, and they follow a very strict behavioral code.
If you suspend these charged rods from a silk thread, a fundamental truth is revealed right before your eyes. Bring a charged glass rod near another charged glass rod, and they physically push away from each other. They repel. But if you bring that same glass rod near the plastic rod we rubbed with wool, they pull toward each other. They attract. It perfectly visually confirms our golden rule: like charges repel and unlike charges attract.
Let's hit section 3, the anatomy of charge. Additivity, quantitation, and conservation.
Electric charge plays by 3 very strict rules. First up is additivity, which just means if you have multiple charges in a system, you simply add them up algebraically, like normal numbers, to get your total. Second is quantization, meaning charge comes in discrete, indivisible little packets. And third is conservation, meaning you can't create or destroy charge. The total charge of an isolated system always remains constant, it just transfers from one body to another.
What's really fascinating here is this concept of quantization. It's a bit of a big word, sure, but the core idea is simple and really profound. It basically means you can't just transfer any random continuous amount of charge. It has to be transferred in whole numbers of electrons. You can transfer 1 electron or 2 or a million, but you can never ever transfer 1.5 electrons. The formula Q equals NE captures this perfectly, where N is an integer and E is that basic quantum of charge.
And what exactly is the charge of that single, fundamental electron, that letter E? Well, it's incredibly small. The notes define it precisely as 1.6 times 10 to the negative 19 coulombs. Guys, that is a decimal point, followed by 18 zeros before you even get to the 16. It's infinitesimally tiny.
So, to test our understanding of this, here's a fantastic question straight from the source notes. It asks, what happens when you run a comb through your hair on a dry day and 10 to the 22nd power electrons jump ship from your hair onto that comb? What is the total charge actually carried by the comb?
Let's look at how the notes solve this using the exact structure we just learned. Step 1, we identify our variables. N is our massive number of moving electrons, 10 to the 22, and E is our tiny elementary charge. Step 2, we apply our quantization formula, Q equals NE. For step 3, we just multiply them together. When you multiply that absolutely huge number of electrons by that incredibly tiny charge, it reveals that the comb holds a surprisingly large charge of negative 1.6 times 10 to the power of 30 coulombs. It's a brilliant example of how microscale physics creates macroscale effects you can literally feel.
Which brings us to section 4, charge versus mass, a head-to-head comparison.
Pitting these two against each other builds our understanding so perfectly. Look, charge can be positive, negative, or zero. Mass, on the other hand, is always positive. You simply can't have negative mass. Furthermore, charge is strictly conserved and totally independent of speed. It doesn't care how fast you're moving. But mass?
According to the special theory of relativity mentioned in the notes, mass actually increases with speed. How wild is that?
So the crucial point here is this duality. Because charge can be positive or negative, electrostatic forces have the dynamic ability to either push or pull. Gravitational forces, which depend on mass, are strictly a one-way street. They only ever pull things together. Gravity attracts, but electrostatics can attract and repel.
All right, final section, number 5, Coulomb's law revealed, the ultimate mathematical engine.
Here we have Coulomb's law fully defined. In plain terms, this law tells us that the force between two charges grows exponentially when the charges get bigger. Makes sense, right? But crucially, that force drops off incredibly rapidly as they get further apart. The distance between them is a massive, massive factor.
Looking at the finalized formula directly from the source notes, we see this relationship beautifully and perfectly laid out. F equals K times Q1 times Q2 divided by R squared. The Q's are the charges, the R is the distance. But pay close attention to that K at the front. That's the electrostatic force constant, and the notes show us that its value in a vacuum is absolutely huge, 9 times 10 to the 9th power. That massive constant means the underlying electrostatic forces are incredibly powerful.
To really ground all this heavy math back in reality before we finish up, the notes provide this mind-bending calculation. Think about a simple 250-gram cup of water. Using Avogadro's number, the notes calculate that this tiny cup contains an astronomical amount of charge, literally millions of coulombs. But we don't get shocked when we drink it, right? Because it is perfectly, flawlessly balanced in equal amounts of positive protons and negative electrons. So I'm going to leave you with this provocative thought to end our explainer today. If a simple, tiny cup of water sitting on your desk is teeming with millions of coulombs of potential electrostatic force tightly bound within its atoms, just imagine the staggering scale of the invisible mathematical rules and electric forces holding the billions of cells in your own body together right now. The beauty of physics truly does lie in its simplicity and in its hidden power. Thank you so much for exploring this with me today.